Hello there! This video is going to help you get a little bit of a refresher on some computations that you've probably forgotten because we've done them a long time ago. And they are things that you are going to need to know how to do on the final cumulative quiz for Psych 210. So I'm going to show you guys how to create a frequency distribution table and graph with raw data. I'm also going to show you guys how to use a frequency distribution table to calculate the mean and standard deviation and find the median, and then how to identify the most appropriate measure of central tendency based on the shape of your distribution and the scale of measurement for your data. Then I'm going to wrap up with some z-score stuff. So going back to a long time ago when you guys were using z-scores to compare two different x values from different distributions, and then also showing you how to use a z-score to figure out what score is at a specific percentile in a distribution. Okay, so let's get started with creating frequency distribution table and graph. So you see a set of scores here, some raw data, and these are just some sample knowledge check scores that I pulled from Canvas. And I want you to first create a frequency distribution table. Now, I'm hoping that you're watching this video having already attempted these problems on your own. If you haven't, stop the video now, attempt this on your own. The best way to know how much you know is to try before you watch me do it. It's easy to sit there and be a passive recipient of me doing problems on the computer screen. But if you're not trying them on your own, you're not really understanding how much you understand. Just but from watching me, you think you understand, but you probably don't know as much as you think you know. Okay, I'm off my soapbox now. Let's go ahead and do some problems. Okay, so let's first create our X column, which is knowledge check scores, and then our F column, which is the frequency, or in other words, how many students had each score. So I'm going to start with the highest and go down to the lowest. My highest score is an 8. And now remember, you go all the way to the lowest score, even if there's some scores that are missing in between. So 8, 7, 6, 5, 4, 3, and 2. Now I'm looking at my data. I don't have any 3s or 4s. I don't care. I'm including them in my frequency distribution table because that'll help me illustrate those gaps in values in my graph. So let's see, we have 2 8s, 2 7s, we have 5 6s, we have 2 5s, 0 4s, 0 3s, and 1 2. So 2 2 5, 2 0 0 1. All right, great. So that's my table. I'm done. Check. All right, now let's look at the graph. So I'm just going to kind of sketch this by hand. And I'm not an artist. Look at that. It's a mess. But that's okay. As long as you get close, I'm happy. So let's see. Let's be specific with how we label our axes and not just put X and F. Let's put number of students. That's what the frequency is based off of. And then knowledge check scores. Make sure that when you are creating your frequency distribution graph, that you label your axes with words and numbers. And not just X and F, but I actually want to know what each axis represents specifically. Okay, so our scores range from 2 to 8, so I'm going to reflect that on the x-axis, starting with the low and going to the high end from left to right. So we have 2, 3, 4, 5, 6, 7, and 8. Okay, and then our frequencies range from 0 to 5, so we'll make our y-axis reflect that. So 0, 1, 2, 3, 4, 5. Now, the word appropriate is a key word. Not just any frequency distribution graph, but the one that's appropriate for your data. Now remember, you have to think about the scale of measurement. If you have a nominal or ordinal scale, then you want to use a bar graph where the bars don't touch. If you have interval or ratio data, then you want to use a histogram or a polygon. I like histograms. I like drawing bars. If you want to use a polygon and connect the dots, it's totally fine with me. So let's go ahead and create a histogram with this data because knowledge check scores are ratio data. They have a true 0 point. If you got a 0, you got none of the items correct. And each value tells you the not only direction, but the magnitude of the differences. So not only do you know that a 4 is a better grade than a 2, but it's 2 points higher. So it's ratio data. Okay, so how many 2s did we have? We had 1. How many 3s? 0. How many 4s? 0. How many 5s? We had 2. Okay. How many 6s? We had 5 of those. All the way up here. 7s, we had 2 of those. And 8s, we had 2 of those. See, I'm inspiring you with my poor artwork so that you know that I don't expect greatness for these. Just a rough sketch. It's pretty sad, but that's okay. All right. Just kind of visualizing the data because I'm going to want to know the shape later. I can kind of draw a line over this. And it's looking rather negatively skewed. Again, this will come into play for the last part of this particular question, where we identify the most appropriate measure of central tendency. All right, next. Calculating the mean, the standard deviation, finding the median, and identifying the most appropriate measure of central tendency. So I'm going to go ahead and recreate my original frequency distribution table. But because I'm using this table to do math, I'm just going to get rid of the 4 and the 3. When you're asked to create a table, I want you to include the full range of x values. But if you're using a table for computations and you have values with zeros, you can eliminate those just to make things simpler. All right, so let's recreate this table. So x, so we're just going to have 8, 7, 6, 5, and 2. And then our frequencies from before. So we have 2, 2, 5, skipping the zeros, 2 and 1. 2, 2, 5, 2, 1. All right. Now, we need to calculate the mean. So for part C, now I'm using m, not mu, because I told you before this is a sample. All right. So the formula for the mean is the sum of x divided by the sample size. Now be careful when you're using a frequency distribution table for calculations. You have to take into account the frequency of each x value when you're computing the sum of x. So remember, the alternate version of this formula that you could use when you're using frequency distribution tables is the sum of each x multiplied by each f, and then your sample size is just the sum of the frequencies. Okay, now keep in mind, you don't have to use the table if you don't want to. You could simply add these scores together to get your numerator and then count how many scores you have to get the denominator. It's up to you. I think that students often opt for the table because they already have it, and I feel like students always make more mistakes with the table. So I'm really just going to focus on computations with the table. But you're more than welcome to try these computations just using the raw data and then check your answers against what we come up with here. Okay, so xf. Multiply each x by its respective frequency. So we have 16, 14, 30, 10, and 2. All right, so that tells us the sum of x. So to find the sum of x, you just add these together. And you end up with 72 for your sum of x. Now, for your frequency piece of this, you want to add those together to figure out the sample size. And 2 plus 2 plus 5 plus 2 plus 1 gives you n equals 12. So I plug those values into my mean formula. So we have, and let me go ahead and scoot that bad boy down. Come here. All right. I'm just going to write the simpler version of the formula because I've done this so many times that I don't need that reminder about frequencies. Okay, so sum of x is 72. Sample size is 12. 72 divided by 12 gives you 6, and that is our sample mean. All right, so the next thing that we need to do for part D is calculate the standard deviation. So I think I'm going to start that over here. And the symbol that I'm going to use for the standard deviation is S. And the formula that I'm going to use is the sample standard deviation formula that has n minus 1 in the denominator because it's a sample. So I'm looking at this formula and I'm like, I know what my sample size is, so I can quickly fill that in. I just found it. It's 12. I don't know what my numerator is, so it's time to write down a new formula. And so the sum of squares formula is sum of x squared minus sum of x quantity squared divided by the sample size. And I'm looking at this and I go, okay, well, I don't know what that sum of x squared is yet, but I do know the second part of this formula. So I have something minus, remember, the second part of this formula looks a lot like the mean formula. It's just that you have a square in the numerator. So 72 squared divided by 12. I need to find that sum of x squared. Now, just like when I had to find the sum of x, I had to take the frequencies into account, I also need to do that when I find the sum of x squared. So the first step, you find the squared version of each x value in your data set. Then you take that value and you multiply it by the respective frequency. So just squaring all my x's. So 8 times 8 is 64, 7 times 7 is 49, 6 times 6 is 36, 5 times 5 is 25, 2 times 2 is 4. All right, so now I need to take each one of these x squared values and multiply it by its respective frequency, or its f value. So 64 times 2 is 128, 49 times 2 is 98, 36 times 5 is 180, 25 times 2 is 50, and 4 times 1 is still 4. Add all those together and I have my sum of x squared, which happens to be 460. So now I can plug that in to the beginning of my formula here. So going through order of operations, the first thing I want to do is figure out what 72 squared is. So I'm just going to recopy everything except for the squared version of 72, and the squared version of 72 is 5,184. Okay, next step. Solve for the division. 460 minus 5,184 divided by 12 gives you 432. And my sum of squares is 28. Now I can plug that in to the formula for my standard deviation. So we have 28 in our numerator. First thing we need to do is solve for the denominator because we don't know what we're dividing by yet. So keep my square root. Don't forget to recopy it down or you will forget it in the end. So we have 28 divided by 12 minus 1 is 11. 28 divided by 11 gives you 2.545. And the square root of 2.545 is 1.595. And that, my loves, is the standard deviation for the sample. So you can say that on average, most scores are within 1.595 points of 6, right? Within one standard deviation of the mean. And if you look at the data, that totally makes sense. That looks like a pretty solid standard deviation. I'm not doubting my calculations. So now let's find the median. So part E here. We're all over the place. We've got C, we've got D. Now let's do E right here. Okay, so for part E, the median. So I'm going to use the median index to figure out what location my midpoint is at, as far as what order it is in the scores. So I've got I equals n divided by 2. Now remember, if you have an odd number of scores, you have a single midpoint. And when you calculate n divided by 2, you'll get something 0.5, and you just round up, and that tells you the position of the median. If you have an even number of scores, you'll have 2 midpoints. You'll get a whole number for your median index. So n divided by 2 will give you a whole number. You take the score at that location and then the score just above it, add those together, divide by 2, you get the median. We so happen to have an even number of scores. So we have the more complicated version of this situation where we have 2 midpoints, we have to find the mean of those 2 midpoints to get the median. So n divided by 2 is 12 divided by 2. We get 6. So we need to go with the 6th score plus the score just above it, the 7th score, and then we divide that by 2. Now, I like to look at my frequency distribution table and just add up my frequencies until I get to a spot where my two midpoints are. So if I just look at my frequencies, so the first two scores, if we start with the high end, are 8s. Then the third and fourth score are 7s. And then the 5th, 6th, 7th, 8th, and 9th scores are 6s. So that includes the 6th and the 7th score, right? So first two are 8, third and fourth are 7, 5th, 6th, 7th, okay, I'm done. Those are 6s. So we have 6 plus 6 divided by 2, 12 divided by 2 is 6. That is your median. You can abbreviate that MDN if you want. So now the question is, which measure of central tendency is most appropriate? Again, you need to consider the scale of measurement, and you need to consider the shape of the distribution. Well, we have a situation where we have ratio data. And we have a situation where we have a skewed distribution. So we would want to use the median because we have ratio data that's skewed. Now, if we had ratio data that was somewhat normal in shape, we would go for the mean. If we had nominal or if we had nominal data, we would automatically go with the mode, and if we had ordinal data, we would automatically go with the median. The only time you have to consider the shape of the distribution is when you have ratio or interval data. Again, if it's ratio or interval, skewed, median, normal, mean. All right, so now let's use z-scores to compare Neil's marathon performance for the Red Rock Canyon Marathon to his performance for the Boston Marathon. Remember, z-scores are great if you want to make comparisons based on scores relative to their distribution, but they're coming from different distributions. It allows you to make an apples to apples comparison with something that started off apples to oranges. After we do that, I'm going to show you how you can use z-scores in the unit normal table to figure out which completion time is at the 75th percentile of all runners in the Boston Marathon. Okay, so let's start with part A. Let's go ahead and simplify this information by writing it down, just the numbers that we need, okay? So we've got the Boston, I'm not going to put BM and abbreviate it because that could be misinterpreted. Let's see, Boston Marathon. Okay, then we have the Red Rock Marathon. Well, let's be specific. Red Rock Canyon Marathon. All right. All right, so let's go ahead and jot down the population mean for each, the standard deviation for each, and then what Neil's actual score was, or his completion time for each. Okay, so for the Boston Marathon, the mean completion time was 4.75 with a standard deviation of 0.25. For the Red Rock Canyon Marathon, the mean completion time was 5 hours with a standard deviation of 1. Now, Neil finished the Boston Marathon in 5 hours and the Red Rock Canyon Marathon in 5.5 hours. Now, if you were just looking at the means, it would appear that the Red Rock Canyon Marathon was better. Or was more difficult, right? Because the mean completion time was longer. Then if you look at the standard deviations, you can see that there was more consistency in the Boston Marathon than there was in the Red Rock Canyon Marathon. So for the Boston Marathon, most people, assuming a normal distribution, finished between 4.5 and 5 hours. Whereas the Red Rock Canyon Marathon, most people finished between 4 and 6 hours. Remember, plus or minus 1 standard deviation from the mean. So based on these two different distributions, which marathon did Neil perform better in relative to the rest of the runners? We need a z-score for that. So z is equal to x minus mu divided by sigma. Or in other words, the raw score minus the mean of all scores divided by how spread out those scores tend to be. So we have 5 minus 4.75 divided by 0.25. This leaves us with 0.25 divided by 0.25, which is 1. Okay, now the z-score for the Red Rock Canyon Marathon. So we have 5.5 as actual score minus the mean of 5 divided by the standard deviation of 1. We get 0.5 divided by 1. We get 0.5 for the z-score. Now be careful when you are answering the part about how you know which marathon he performed better on relative to the population of runners. Now, if we're measuring something where higher scores are better, then you want large z-scores, right? Large z-scores indicate better performance. But if you're measuring something where smaller scores are better, so quicker running the marathon, right? A lower completion time, then z-scores that are lower indicate better performance. Imagine if Neil finished below the mean, right? Then he'd have a negative z-score, and that's even more desirable because that means that he was faster than most people, depending on how low his z-score was. Okay, so in this case, this is the more desirable result. The Red Rock Canyon Marathon has the lower z-score, so that's how you know that relative to the rest of the marathon runners, he did better in the Red Rock Canyon Marathon. So now we're ready to find out, based on the z-scores in the unit normal table, what completion time is at the 75th percentile of all runners in the Boston Marathon. Okay, so the first thing I want to do is kind of visualize what this would look like. So I'm going to draw my normal distribution. We're assuming that it's normal. First, I want to kind of sketch out my percentiles, with 0 being at the far left end and 100 being at the far right. Remember, percentile tells you the percentage of scores that are equal to or less than a specific score. So if you're at the 100% percentile, that means that all scores, 100% of the scores, are less than or equal to your score. Now in the middle is the 50th percentile. The 50th percentile is always the median, but because in a normal distribution, the mean, median, and mode are equivalent, then the 50th percentile represents the mean. And the population mean that we're working with for the Boston Marathon is 4.75. So that goes right in the middle here. And what z-score will 4.75 have? 0, right? The z-score for the population mean is always 0. The z-score tells you how many standard deviations away a specific score is from the mean of all the scores. And if your score is equal to the mean, then you're 0 standard deviations away from the mean. So your z-score is 0. So just kind of sketching this out, the 75th percentile would be about here. And that separates the top 25%, or p equals 0.25 in the tail, from the bottom 75%, or p equals 0.75 in the body. So we're presented with a situation where we know the p-value. We need to use the unit normal table to compute, or to find z, and then use the z-score to compute x. So we need to go to the unit normal table and either find p equals 0.25 in the tail or p equals 0.75 in the body. That'll lead us to the z-score that we need to then calculate x. I'm going to go ahead and go with the body first. So I'm looking for the closest thing to 0.75 in the body. This value is just above 0.75. This value is just below. This value is 0.0014 points away from 0.75. This one is 0.0017 points away from 0.75. This value is technically closer. That leads me to a z-score of 0.67. Now if I went with the tail and found 0.25 in the tail, I still land on a z-score of 0.67. This is the closest thing to 0.25 in the tail in my table. And I know that it's positive 0.67 because I am working with a percentile above 50. Or, in other words, I'm looking for a score that's above the mean. If I was looking for the score at the 25th percentile, then my z-score would be negative 0.67. I'd still be looking for 0.75 in the body or 0.25 in the tail if I was looking for the score at the 25th percentile, but it would be over here, so it would be a negative z-score. So just keep that in mind. Okay, so my z-score is equal to 0.67. So let me go ahead and use the x formula to figure out what x value represents a z-score of 0.67. So remember, the z-score tells you how many standard deviations away your score is from the mean. So you take the z-score, multiply it by the standard deviation, and in this case you get how many hours away the score at the 75th percentile is, how much above the mean that is, because your z-score is positive. So you add that to your mean and then you got your score. So z 0.67 times standard deviation for Boston Marathon was 0.25 plus the mean for the Boston Marathon for 0.75. So 0.67 times 0.25 is 1.68, and then you add that to, 0.168. 0.168 plus the mean of 4.75, and you end up with 4.918. That is the x value at the 75th percentile. So based on this, you could say that 75% of runners in the Boston Marathon had a completion time of 4.918 or lower, right? And conversely, 25% of Boston Marathon runners took longer than 4.918 hours to complete the marathon. So I hope this was a nice refresher for you, and I hope that you practiced these or tried these before you watch the video, and I hope you guys do really, really well on that final quiz.